I want you to close your eyes for a second. Well, unless you're driving, in which case, please keep your eyes on the road.
Mm.
But I want you to imagine holding something small and incredibly dense in the palm of your hand.
Okay.
It's a geometrically immaculate cube, like really sharp along the edges, flat on the faces. And it is glowing with this ethereal, pale, ice blue light.
Yeah, if you saw a picture of this object out of context, it honestly looks like a prop from a sci-fi movie.
Right.
It's like some kind of alien energy source or, a hyper-advanced data crystal waiting to be plugged into a mainframe.
Exactly. You look at this glowing blue cube, and you just assume it has to be synthesized in a high-tech lab under, super strict parameters.
But it's not.
No, it's not. It is completely natural, pulled straight from the Earth.
Right.
And the most striking part about this futuristic-looking, mathematically precise blue crystal is made out of the exact same chemical compound you sprinkle on your French fries.
Yeah.
It's salt.
Sodium chloride, or halite, to use the formal mineralogical term. But it's a very specific, incredibly rare manifestation of halite, one that requires a deeply paradoxical set of environmental conditions to actually form.
Well, welcome to today's deep dive.
Mm-hmm.
Today we are looking at a single, frankly fascinating source text. It's a collection of excerpts from a comprehensive geological survey called The Luminous Geometry of Tuzluca Blue Halite.
Great paper.
It really is. And our mission for this deep dive is to trace the dramatic million-year journey of how perfectly ordinary ancient seawater transformed into one of the most, visually stunning, fragile, and geometrically unblemished records of deep time on planet Earth.
Because the creation of this mineral is a phenomenal narrative of extremes. You don't just get a pristine, translucent blue cube of salt by chance.
Definitely not.
It demands a sequence of geological events so precise and frankly so contradictory that its mere existence is a marvel. I mean, we were talking about oceans boiling away into nothingness, continents colliding with unimaginable force, and atomic structures being silently warped by invisible background energy over millennia.
Okay, let's unpack this. Because I read the source material, and the timeline required to create the cube you're imagining in your hand is just staggering. To understand it, we have to go back to Eastern Turkey, millions of years ago.
Right.
And back then, the landscape did not look anything like the mountainous, rugged, high-altitude terrain we see today. We are talking about a completely different planet, geographically speaking.
Yeah, the region that is now Eastern Turkey was essentially a vast basin.
Like a giant bowl.
Exactly, and it was covered by massive, shallow inland seas. This is a period when the climate was intensely volatile. The Earth was experiencing these severe atmospheric shifts, which caused these inland seas to undergo relentless, punishing cycles of evaporation and inundation.
So the water would just bake.
Basically, yes. The basin would bake under searing sheet until the water completely dried up, leaving a totally barren expanse. Then, eventually, the climate would shift again, the waters would breach the basin, and the sea would return.
And this wasn't just a one-time thing.
Oh, no. It happened over and over again across vast expanses of geological time.
And the physics of an evaporating sea are so fascinating because when that water vaporizes into the atmosphere, it leaves all its dissolved baggage behind.
Right.
Like the water turns to gas, but the dissolved minerals are stranded.
This is the fundamental mechanism behind evapominerals. When a massive body of salt water evaporates, the concentration of dissolved elements spikes.
They get super salty.
Exactly. They reach a point of supersaturation where the water simply cannot hold them anymore, so they precipitate out, turning solid, and settle onto the basin floor.
And they do it in a specific order, right?
They do. It's very predictable based on their solubility. First, the least soluble minerals drop out, like carbonates. Then the sulfates, like gypsum. And finally, when the water is almost entirely gone, the halite, your sodium chloride, precipitates out in massive, thick sheets.
Just thick crusts of salt.
Yeah, and the source specifically knows this basin was really rich in halite, alongside layers of gypsum and potash.
Imagining millions of years of this extreme drying and refilling cycle makes me think of nature building a massive, highly pressurized geological layer cake.
That's a good way to picture it.
You have a thick foundational layer of halite crust. Then the sea returns, perhaps washing in a layer of silt or mud. Then the sea boils away again, laying down another thick strata of salt, followed by more sediment.
And that cyclical layering creates the foundational architecture of the Tuzluca deposits. As the millions of years march on, those alternating layers of salt and sediment are buried.
Because the Earth is always shifting.
Right. The tectonic plates shift. sea levels change permanently, and the ancient salt beds find themselves trapped beneath millions of tons of younger, heavier rock. The sheer weight of the overlying earth compacts and compresses the layers, preserving them as a massive, continuous subterranean salt formation.
Which makes logical sense. I can picture a giant subterranean block of crushed salt buried deep under a mountain range. But here is the massive contradiction that the source text brings up.
The geometry.
Yes. Because if I'm picturing this layer cake analogy, what we have is just a compacted, dense wall of underground sea salt. It's a solid, crushed mass. So this is just a giant underground block of compacted sea salt. How do we get to individual, pristine crystal cubes?
It seems impossible.
It really does. The text notes these cubes look as if they were cut by nature itself. You cannot get flawless geometric isolation by just crushing salt under a million tons of rock.
You absolutely cannot. And this is where the geological narrative abruptly shifts from the slow, quiet, cyclical process of evaporation and burial to an era of extreme, sudden violence.
Right.
To extract pristine, isolated crystals from a compacted, solid block of evaporate, you need a catastrophic disruption.
And the region definitely experienced one. The Tuzluca salt beds were caught in what the text describes as a complex multi-plate traffic jam.
Yeah, we are looking at one of the most volatile tectonic collision zones on the globe, the convergence of the Anatolian, the Arabian, and the Eurasian tectonic plates.
Which is just massive.
These are titanic slabs of the Earth's crust constantly grinding, pushing, and tearing into one another.
To put the scale of that into perspective, it's not just a minor shifting of dirt. We're talking about a planetary-scale hydraulic press. You have continents acting as the crushing plates.
The forces are just incomprehensible.
The geological pressure exerted on these buried salt beds during that collision must have been wild. But the pressure didn't just crush the salt further, it fundamentally altered its environment. The text explains that salt, under tectonic pressure, acts very strangely.
Doesn't always just shatter.
Right.
Salt actually has a property called diaporism. It is surprisingly plastic under slow, immense pressure. It can flow almost like toothpaste.
Wow.
But when subjected to the sudden, violent fracturing of tectonic collision, the surrounding rock strata rupture and warp. In the Tuzluca region, this immense shifting, folding, and grinding created something miraculous within the host rock.
These little sealed pockets.
Exactly. Sealed, completely protected voids, subterranean pockets and veins that opened up deep underground and were instantly sealed off from the surrounding environment.
I picture them as little subterranean safe rooms, totally isolated from the chaos, tearing the crust apart around them.
That's a perfect analogy. And inside these newly formed, hermetically sealed pockets, highly concentrated saline fluids, essentially hypersaline brine that was trapped in the surrounding rock, were able to pool.
Just gathering in the dark.
Right. Because they were completely insulated by the thick rock walls of these veins, these fluids began to cool and concentrate at an agonizingly slow pace, completely undisturbed by the outside world.
Wow.
If we connect this to the bigger picture, the irony is profound. You have this incredibly chaotic, violent geological crash zone tectonic plates literally building mountains and tearing the earth apart, and yet it is that exact violence that creates the ultimate stable environment.
Because it opened up those safe rooms.
Yes. The tectonic rupture creates the perfect, quiet womb necessary for flawless geometric growth. Because the fluid in those pockets cooled so slowly over such immense stretches of time, the sodium and chloride ions weren't rushed.
They can take their time.
They had all the time in the world to arrange themselves into their absolute optimal natural state of lowest energy, which is a mathematically precise symmetrical cube.
I have to point out an amazing paradox here, though, because the source text makes a big deal out of how evaporates normally behave.
Oh, absolutely.
Evaporates, by definition, usually grow relatively quickly compared to other minerals. Like when water evaporates on the surface, the salt crystals just kind of crash out of the solution fast, forming these messy, interconnected, cloudy crusts.
Right, they're usually opaque and chaotic.
But the Tuzluca halite cubes are exceptionally clear and exceptionally large. It's a staggering contradiction. The analogy that comes to mind is trying to build an immaculate 10-story house of cards in the middle of a professional wrestling match.
I love that. The tectonic collision is the wrestling match. Everything is vibrating, shattering, and deforming.
Exactly. But somehow, these isolated fluid pockets were so perfectly insulated, so structurally secure, that the house of cards, the crystal lattice, could be built atom by atom, ion by ion, without a single vibration knocking it out of alignment.
The extreme clarity of the Tuzluca halite is a direct testament to the stability of those sealed safe rooms.
It's amazing.
The crystal lattice grew without any rapid temperature fluctuations, without any rushing of the precipitation process, and without any physical agitation. It is pure mathematical order asserting itself in the dark over thousands of years.
Okay, so the safe rooms explain the immaculate geometry, and the slow cooling explains the clarity. But this brings us to the most glaring question of all.
The color.
The absolute core of this deep dive. The text specifically focuses on Tuzluca Blue Halite. If I go to my kitchen cabinet right now, salt is white. Or, if it's a large crystal, it's totally transparent. If these underground pockets were completely sealed off from the outside environment, and the crystal is growing from pure trapped brine, what is physically painting these cubes blue?
This is where we have to leave geology behind and transition into solid-state physics.
Okay, here we go.
Because our intuition about colored minerals is usually based on chemistry. When we think of colored gemstones, rubies, emeralds, or even the pink Himalayan salt on a fancy dinner table, the color is almost universally caused by a chemical impurity.
Like a foreign substance getting mixed in.
Exactly. A trace element, foreign to the host mineral, that got trapped in the crystal lattice as it was forming.
I'm tracking with you. A little bit of iron slips into the mix and makes a mineral red, or a trace amount of copper makes it green. The mineral is basically dyed by its ingredients.
But the Tuzluca Blue Halite totally shatters that intuition. The Geological Survey is emphatic on this point. The blue coloration in these specific halite cubes is entirely independent of chemical impurities. There is no trace copper, no iron, no cobalt tinting the salt. Chemically speaking, it is exceptionally pure sodium chloride.
I'm trying to picture the physics here. If there is no chemical dye, no foreign element trapped inside, and the crystal is sealed inside a solid rock vault miles underground, the only thing that could be altering its appearance is something that can pass straight through solid rock.
Which is?
Are we talking about radiation?
We are. It all comes down to natural background radiation. The geological strata surrounding these salt formations, often potassium-rich rocks or specific shales, naturally emit very low, steady levels of gamma radiation.
Just constantly cooking the salt.
We're talking about persistent, low-dose exposure sustained over millions of years. What's fascinating here is how that radiation interacts with the salt without changing its chemical identity.
How does it do that?
As the gamma rays bombard the halite crystals, the energy literally knocks an occasional chloride ion completely out of its place in the immaculate crystal lattice.
It just ejects it from the structure.
Yes. It creates a microscopic void, a vacancy in the lattice. But nature abhors a vacuum, especially an electrical one.
Right.
To maintain the electrical neutrality of the crystal, a free electron slips into that empty space where the chloride ion used to be. This trapped electron is what physicists call an F-center.
An F-center.
Yeah, from the German word Farbzentrum, which translates to color center.
Here's where it gets really interesting for me, because this explains the optical illusion perfectly. The salt isn't dyed blue by a mineral. It's basically bruised by radiation.
Bruised is a brilliant way to conceptualize it. The radiation is inflicting microscopic structural trauma to the lattice.
I think of it like a pristine glass prism. Normally, light passes cleanly through it without being absorbed. But if you put a microscopic scratch deep inside the glass, suddenly the light hits that flaw, gets absorbed or scattered, and casts entirely different colors.
That's spot on.
When light enters the Tuzluca halite, these electron traps, these color centers, interact with the photons. The track electron absorbs the lower energy, longer wavelengths of light, like the reds and the yellows.
Right.
But it allows the high energy, short wavelengths to bounce back to our eyes. And those short wavelengths are blue.
The mechanism is elegant in its complexity. The light is literally being filtered by the empty spaces where atoms used to be. And the source text points out that the resulting color isn't uniform.
Oh, it varies.
Yes, it can range anywhere from a very pale, ghost-like ice blue to a deep, profound indigo. That spectrum depends entirely on the defect density, how many electron traps there are, as well as the clarity of the host crystal and the stability of those internal bruises over time.
So more bruises mean a darker blue.
Exactly. The deeper the indigo, the more intense the structural distortion.
The poetry of that is wild to think about. You have this profound marriage of absolute mathematical symmetry, the unblemished, precise cubic geometry on the outside paired intimately with this internal microscopic damage.
It's beautiful.
The structural perfection allows it to form a pristine cube. But the radiation damage is what makes it blue.
It is a striking dichotomy. And it's crucial to recognize that this structural distortion, the very physics that give the halite its luminous, ethereal glow, is intricately tied to the physical reality of the mineral itself.
Which brings us to perhaps the most sobering aspect of the Tuzluca halite analyzed in the survey.
Its extreme physical vulnerability.
Yes.
We absolutely need to touch on that. Because when you look at high-resolution photos of these dark blue cubes, they look dense. They look like sapphires.
They look indestructible.
They look like you could drop them on a concrete floor and they dent the concrete. But they are incredibly delicate. The text mentions they have a Mohs hardness of only 2 to 2.5.
To put that into practical terms, with a Mohs hardness of 2, this crystal is so soft you could easily score the surface of it with your own thumbnail.
Just scratch it right up.
Yeah. Despite its imposing visual presence, it lacks the structural fortitude of almost any other gemstone. And it's not just soft. It is highly soluble. It will literally dissolve in water. If you took this million-year-old radiation-bruised geological marvel, a stone that survived the crushing weight of continental collision, and simply dropped it into a glass of tap water, it would vanish.
It would melt away into standard salt water.
Which serves as a stark, visceral reminder of its origins. This extreme fragility is a direct physical echo of the fact that this mineral was once entirely fluid.
It was an ancient sea.
Right. In geological terms, it has only recently stabilized into a solid architectural form. It is in a constant state of tension, desperately wanting to return to its liquid state.
So what does this all mean for you?
Yeah, if you're listening to this, you might be wondering, why dedicate a deep dive to a lump of fragile, bruised blue salt from eastern Turkey?
Because of what it represents as an artifact.
Exactly. The source text refers to Tuzluca's salt deposits as a living archive of Earth's climatic history. When you conceptualize holding a piece of this halite, you're holding a literal tactile record of planetary transformation.
Every single cubic specimen is a high-fidelity snapshot of an ancient ocean. It is a volume of water that was trapped, desiccated, buried beneath continents, crushed by the grinding tectonic plates of the Anatolian convergence, isolated in a subterranean vault, and bombarded by invisible radiation for millennia.
It's the ultimate journey from sea to stone. From a chaotic fluid to a rigidly disciplined structure, you're holding a frozen, bruised piece of a long-dead ocean.
It really is incredible to think about.
And the blue varieties we've discussed today are just the rarest, most improbable expressions of that history moments, where the physical and environmental conditions aligned with such mathematical precision that they produced both the structural purity to form the exact cube and the optical distortion to paint it blue.
This raises an important question, I think, about how we define permanence in the natural world. Human intuition tells us to look at rocks and minerals as the ultimate symbols of endurance and immutability.
As solid as a rock.
Exactly, but the Tuzluca blue halite directly challenges that assumption. This solid geometric stone is actually just a temporarily paused liquid. It is a fleeting, vulnerable moment of solid geometry caught in the middle of an ocean's endlessly fluid life cycle.
It fundamentally reframes how you look at the deep earth.
Okay.
To wrap up this incredible geological journey, the Tuzluca blue halite is far more than a visual oddity. It's a profound survivor.
Absolutely.
It was born from the volatile evaporation of ancient shallow seas under a scorching sky. It was buried, then caught in the crushing, violent tectonic vice of colliding continents. It found miraculous shelter in sealed subterranean safe rooms, slowly assembling itself into pristine mathematical cubes over eons.
And finally, it was given its signature luminous blue color, not by chemical dyes or trace minerals, but by the invisible microscopic bruising of natural radiation knocking its atomic lattice out of alignment.
The narrative of this mineral is a masterclass in the immense complexity of earth sciences. It demonstrates that natural beauty is rarely a straightforward process.
It is invariably the result of deep time, unimaginable physical forces, and incredibly delicate microscopic balances.
Thank you for joining us on this deep dive. It's a humbling reminder that the world beneath our feet is constantly, quietly writing its own history, sometimes in the form of glowing, flawless blue cubes hidden miles in the dark.
And often, the most extraordinary physical records of that history are also the most vulnerable to erasure.
Which actually leads me to one final thought for you to chew on today. We've talked extensively about how this blue halite dissolves entirely upon contact with water, and how its ethereal color depends entirely on the exact stability of its internal atomic defects.
Right.
We know the climate is shifting again, and the Earth's crust is never truly at rest. If future tectonic movement or a changing surface climate eventually causes groundwater to breach those deep, historically sealed pockets in the Tuzluca region, these ancient blue archives of Earth's history wouldn't shatter under the pressure or fossilize into harder stone.
No, they wouldn't.
If the water returns, millions of years of luminous mathematical perfection will simply dissolve back into the dark, erasing itself without a single trace.